Hello, my name is Orlagh Creevey. I'm an astrophysicist at the Observatoire de la Côte d'Azur in Nice, in France. Today I'm going to present to you a simple guide to astrophysical parameters in Gaia DR3. I'm presenting this on behalf of all of my Gaia DPAC colleagues, which are over 70 members, all of whom have participated actively in making the Gaia Data Release of astrophysical parameters available to you. This presentation has been prepared also by my colleagues Rosanna Sordo from INAF in Padova in Italy, and Ulrike Heiter from Uppsala University in Sweden. I give you a very brief picture of many of the Cu8 members who are responsible for making this possible. Okay, so let me begin. Let me begin with the executive summary. So astrophysical parameters, which I will call AP, were produced by the Astrophysical Parameters Inference System, or Apsis. We produce astrophysical parameters, basically probabilities and classifications, outlier object analysis, redshifts of extra-galactic objects, and many stellar parameters such as spectroscopic parameters, evolutionary parameters, etc. So in a nutshell, in Gaia DR3, there are 538 archive fields. Many of these are in the main table astrophysical parameters, along with 9 other parameters and 9 other tables, which include 2 data link tables that you will not see directly on the archive. For Gaia DR3, this is the output of 13 Apsis modules, which processed the BPRP and the ORVS mean spectra to provide a total of 43 primary astrophysical parameters, and then, of course, auxiliary parameters to go along with these. So where do you find it? On the archive, you can go to this email address, this web address, and in 2 main directories, Astrophysical Parameters and Extra-galactic. So you will see the drop-down menu in Gaia Data Release 3. You will see all of the different directory structures. And within the Astrophysical Parameters, there are a total of 6 tables in there. There are also another 2 tables in the Extra-galactic directory. Now, for the rest of my talk, most will be in the Astrophysical Parameters table, unless otherwise specified. Okay, so what I'm presenting today is a brief overview. All of the details will be found in many of these references that I'm showing here. So the first one is the online documentation, and then there are 3 Apsis papers describing the first one, overview of methods and content, the second one focusing on stellar parameters, and the third one focusing on the source classification and non-stellar parameters. Additionally, there's also information in the Gaia DR3 catalog validation, and there are more details for specific modules in these 3 papers that I show on the bottom. Now, if you cannot find the answer to your question, don't hesitate to send your question afterwards to Gaia helpdesk at cosmos.esa.int, and they will forward us your request. Also, we would be interested in getting feedback from you. So when you have used the archive, if you have anything to let us know that we can improve for Gaia DR4, we'd be happy to hear it. At the end of this webinar, I will be available to stay for a couple of questions. So if you want, you can add a few questions in the comments. I may not have time to answer them all today, but we will get through them when we can. Okay, so let's begin with the Astrophysical Parameters Inference System, which is called Apsis. So here I'm showing the data flow of the data flow from the upstream Gaia data all the way through the Apsis. And you can see that it is composed of many different modules. So in the top part, we have the modules that look at source classification or outlier objects or extra-galactic objects. In the second lower part of the table, there are many modules working on the stellar parameterization. And the reason I show you these is because the names, the short names here, you will find in the actual archive field names. Now, just a little focus on the stellar parameters. Here I'm showing a Heitor diagram, and I have many boxes, and basically the boxes are showing you the overlap in parameter space of the stellar modules. Now, each of the modules do different things, either use different data or different methods or different models to produce different parameters. So the input data to Apsis comprises the astrometry, but also the spectra, but it's the mean RVS spectra. So we have results on primarily 6 million sources from the RVS spectra, and the mean BP-RP spectra for a total of 1.6 billion sources. We also use the mean photometry. We note that the G magnitude has been corrected as recommended in EDR3. I would just like to make a point that this is the mean photometry, so if your source is extremely variable, you should take this into account before using the parameters. So on the bottom diagrams, I'm showing examples of the BP-RP spectra. So the BP and RP span from 400 to just over 1,000 nanometers. And the figure on the left is showing how the spectra vary with the effect of temperature. And the figure in the middle panel on the bottom shows how the spectra vary as extinction varies. So you can see that these are two primary astrophysical parameters that we can derive from these spectra, but of course it means that we may have some correlations in our results. On the right, I show an atlas of the RVS spectra. So these are just examples of RVS spectra that we have been processing to produce astrophysical parameters for you. For the models, okay, along with the data, we also need to have some models. So we use synthetic BP-RP fluxes from primarily 5 model families, the Marks, Phoenix, A, OB, and BT Settle. We also use synthetic RVS fluxes from the Marks, A, and OB. We also have some empirical training data for these modules that I mentioned here. And then we use simulated BP-RP fluxes. So we take into account the Gaia instrument model and the dispersion law, along with the extinction curve by Fitzpatrick. So on the right panel, in the top, I'm showing how the simulated data, so not the simulated spectra, not the data, vary as a function of temperature and extinction. And then on the bottom panel, I'm showing several different types of objects and how they would look with these, in these simulated data. For example, there are some hot stars, a cool star, a white dwarf, a galaxy, a QSO. On top of this, we then also use bolometric corrections to produce the luminosities, and we also use some stellar evolution models, primarily for 2 of the modules. Okay, so for the rest of my 20 minutes of talk, I'm going to actually describe what's in the archive. So if you are not interested in any part of this, you can skip or come back to it. So I will go through it like this: probabilities and classification, then outlier analysis, then galaxy and QSO redshifts, then interstellar medium and distances, and then I will focus on the stellar parameters. So the parameters from BP-RP, then RVS, then chemical abundances, and then evolutionary parameters. And then in my final slides, I will just give you a very brief overview of what we can do with these parameters from the performance verification papers that have been published. So let me begin with probabilities and classifications. So these come from various modules. And the first one I'm explaining today is on object classification for 1.6 billion sources. So you will find class probabilities along with class labels. These are derived by DSC, and then you have there are a choice of methods that you can choose to investigate, and these will just basically give you a probability if the object is a star, a galaxy, a QSO, binary, or white dwarf. Now there is also in the extra-galactic tables there is also a class label. So this will say if it is a quasar or a galaxy, and there is a second class label called joint, which is a much higher purity of being in that table. The second type of classification is what we call a neuron. So from DSC, there were the 56 million sources that were the worst classified sources, were then analyzed by the outlier analysis team in a self-organizing map. And they produce neurons, so they cluster all of these outlier objects into 30 by 30 different neurons. So you will also find this information in the astrophysical parameters table, but there are more information from outlier analysis, which I'll explain in the next slide. Other classification includes emission line stars for over 57,000. You will find class probabilities from the ESPELS work module. And they classified as a BE star, Herbig star, T Tauri star, DME star, WC star, etc. They also provide a class label to go along with these probabilities. And then finally, for the classification, we also have spectral types for 218 million sources. So this includes a carbon star type, and then the classic OBAFGKM. And this also comes along with a flag. So the flag for ESPHS, if you look at the second digit, the B, this will tell you the quality, where 1 is the highest quality and 5 is the worst. And the number 0 is reserved uniquely to classify it as a carbon star. Now let's move into the object outlier analysis. So I mentioned the last slide, you will find some results in the astrophysical parameters on a source-by-source basis, but then there are also 2 extra tables. So the first one is the multi-dimensional table OA neuron information. So it's a 30 by 30 by n parameters, where n is up to 72 different statistical properties. So in this figure on the right, I'm just showing the class label, which is one of these properties. And you can see that it groups the neurons according to what kind of class it is. In the second table is the OA neuron XP spectra table. And these are prototype template spectra for almost all of these neurons. So in this figure, on the dash line shows the template spectrum. And then the other spectra are basically the XP spectra of all of the sources that fall within that neuron. There is also an online tool available to help you explore these data, and you can load the DR3 catalog directly in there and explore it easily. So now let's move on to the galaxy and the QSO redshifts. So from astrophysical parameters, there are 6.6 million QSO candidate and 1.4 million unresolved galaxy candidate redshifts. And you find these in the extra-galactic tables, so the QSO candidate and the galaxy candidate tables. And the parameter is the redshift. So either from QSOC, which derives the QSO parameters, or from UGC, which derives the unresolved galaxy redshifts. So on this diagram, I'm showing the distribution of the QSO candidates for redshift on the top panel, and then as a function of G magnitude on the bottom panel. There are several different colors and line styles here, and these are basically for different flags and z-score types. So you should look at the documentation to get more information on the best way for you to select your sources. Then now on the right, I'm showing the results from the galaxies. So in the top panel, I'm showing the magnitude distribution of the redshifts of the unresolved galaxies, which go from 0 to 0.6. And then in the bottom panel, I'm showing a comparison of the redshifts derived from UGC directly with those from the SDSS DR16 catalog, showing quite a good agreement. Now let's move on to the interstellar medium and distances. Okay, so the extinction parameters are derived from the analysis of the BP and the RP spectra, and as I mentioned before, this of course can be correlated with effective temperature. And it's also derived from the RVS through the diffuse interstellar band analysis. Okay, so the parameters that you will find in the archive are A0, AG, ABP, and ARP, which are all the extinctions in several bands, except for the A0, which is the one that's defined at 541 nanometers. You will find these results for 3 different modules, GSP FUT, ESPHS, and MSC. On the right, I give you a brief overview of the differences between these modules. So GSP FUT is the general parameterizer, which analyzes all sources to 19 magnitude. It analyzes the results using 4 different models, and these are provided in the astrophysical parameters subtable, whereas the best result per source is found in the astrophysical parameters, and it is also copied to Gaia source for convenience to the users. The ESPHS focuses on the hot stars, so this means more than 7,500 Kelvin. And it also uses the RVS if it is available. So some results are based on both BPRP and RVS, and you will find that information in the flags. Then the MSC is the multiple stellar classifier, and it makes a supposition that what we observe is the combination of 2 components of an unresolved binary. So there would be the same distance and the same extinction, but we'll have individual temperatures and log Gs. So along with these parameters, you can also find EBP minus ORP from GSP foot. You can also find distances from both GSP foot and MSC. And along with this, there are the two data link tables, which are called the MCMC samples from GSP foot and MSC, which provide the Markov chain, Monte Carlo samples for all of the stellar parameters for a subset of the chain. Okay, here I'm showing again how the extinction varies with in the BP and ORP spectra. And if we focus now on the ORVS spectra, there is the diffuse interstellar band that you can see in this diagram here. And this is 862 nanometers. The parameter that you will look at is the DIB parameter. So there are several words associated with the PO2QF and the equivalent width, which are all the fitting parameters of the DIB along with the quality flag. And then finally, for extinction, you will find a 2D total galactic extinction map. You will find two of them. So one of them is at HEALPIX level 6, 7, 8, and 9, and the second one will be at the optimal HEALPIX level. And this uses the A0 from GSP foot, so only sources that have up to magnitudes of 19th, but of course those that trace, that are giants that trace outside of the galaxy. You're encouraged to avoid using the latitudes, absolute latitude below 5 degrees there, because there are not enough tracers in order to be able to do reliable extinction, total galactic extinction. This table has also been integrated into the dust maps Python package. So if you want to do a query by longitude and latitude, you can go directly to the dust maps package and you can install it. You can find it from there. Okay, so now I'm going to move on to the spectroscopic parameters. I will begin with the BP and the ORP parameters. So I have two slides on these. So let's start with the classic atmospheric parameters, which are temperature, TFF, and log G. And these are derived from the same GSP foot, ESPH, and the multiple stellar classifier as well. But on top of this, we also have the metallicity, which is derived from GSP foot and the ESPHS, along with the temperature from the ultra-cool dwarfs. Okay, so UCD, again, is ultra-cool dwarf, which only looks at stars that are cooler than 2,500 Kelvin, but allowing for a margin of error, you could find results up to 2,700 Kelvin. Okay, so let's start with the GSP foot results. So here I'm showing a HR diagram showing a temperature and the absolute magnitude that you will find also in the archive, again, for only sources up to magnitude of 19. And you can see that they have temperatures all the way up to 50,000 Kelvin. So on the bottom panels, you can see there are, I'm showing a comparison with the surface gravities with external data. So on the panel on the left, the top panel, is a comparison with the astroseismic surface gravities. For the main sequence stars, which are the blue, you can see there is excellent agreement and with the astroseismic values. For the giants, the precision is worse, but this is also expected. These are giant stars which are harder to derive. And then in the bottom panel, I'm showing the comparison of the effective temperatures with those from RAVE DR6, where the sign is basically agreement in temperatures, and then we have some more deviations. So I mentioned that along the galactic disk, there are some regions where we will have more biases in temperatures, primarily due to the extinction problems, the extinction correlations. The metallicity is also derived by GSP foot. There is a global offset of about minus 0.2 dex, and then at the lower metallicity is a little bit less reliable. So there has been a calibration tool that has been proposed by the team, and you can find this and download it on the GitHub. Now let's move to the hot stars analysis. So again, there's temperature and log G. So in the first diagram from the hot stars, I'm showing the Kiel diagram of these stars, and these are derived using BP, ORP, plus the ORVS spectra, and you can also find the same for the BP and the ORP. Then on the right panels there, I show a comparison of the surface gravities compared to external data where the median offset is the highlighted orange line in the center. And you can see that between 10 and up to 50,000 Kelvin, we have a relatively good agreement. There are some regions a little bit more difficult to derive, or at least in comparison with the external catalogs. And the two figures are differentiated by their temperatures, or the catalogs that are used. Okay. Now let's move on to the second slide of the BP and RP. So here I show a comparison of the effective temperatures for the ultra-cool dwarfs compared to the literature values. And you can see that there is an overall good agreement between all of these parameters. They also provide a quality flag labeling of 0, 1, and 2. And the 0 are the black dots, the gray are the 1, and the 2 are the light gray symbols. Whereas 0, of course, is the highest quality. Now, there is also the multiple stellar classifier. So I show here a comparison of the effective temperature 1, which is of the brightest component, and the effective temperature 2, which is the other component, compared to the same results from Gala. So you can see the one line is also highlighted, which ideally, if we have the same data and we have the same methods, we get the exact same results. So the color code I'm showing is the posterior probability, so with green being a higher probability. So you can see that we have quite good agreement with external catalogs for the multiple stellar classifier. So the MSc has analyzed all of the stars down to 18.25, so it supposes every single star is a combination of two components. So there will be objects in there that may not be binaries, and there will be some that are binaries. And the luminosity ratio is between 1 and 5. So in this second diagram, I just show the comparison between the two surface gravities compared to the comparison of the temperature of both components. So you have an idea of the parameter space that is covered by these by MSc. Then finally, for the spectroscopic parameters on BP or P, there are also equivalent width of the H alpha line. Okay, so in this figure, I'm showing what's called the pseudo-equivalent width, which is defined in the documentation and the papers as a function of effective temperature. So the very middle panel is what you will actually find in the archive. And the reason I show the other panel, the panel on the left, is because, in fact, when it's measured, it depends on the effective temperature. And so there was a model, a part of the model was subtracted from the lower temperature stars. And this is all detailed in the documentation and the papers. Okay, so let's move on to the spectroscopic parameters from RVS. So the classical parameters for about 6 million stars down to approximately magnitude of 15. And they are temperature, surface gravity, metallicity, alpha over iron, and there are some flags. And these are derived by one main module, which is the GSP spec, but there are two flavors. There's the GSP spec Matisse-Gauguin, which is what I'm showing in the top right, and you'll find them in the astrophysical parameters table. And then there's the GSP spec ANN, which is the neural network version, which you will find in the astrophysical parameters subtable. So on the right panels, I'm showing a comparison of temperature, surface gravity, and metallicity with the literature. And you can see that there is quite good agreement with the literature for these parameters. There is a slight offset in surface gravity. And so the team have proposed a log-G calibration if this is of interest to your science case. So you should check the paper for this calibration. They also propose a calibration for the alpha over iron. They've also done a lot of work on the flags, and they propose a long flag of 41 digits in the first table and 11 digits in the second table, where it gives you very precise information of the quality of the parameter or the abundance, you should look at this if you want, depending on your use case. In the bottom panel here, I'm just showing a comparison of the surface gravity from the astrophysical parameters subtable. So this is the ANN method, and this is for several different signal-to-noise ratios. And as you can see, as we get to lower signal-to-noise ratio, of course, the dispersion gets a little bit worse. But for the higher signal-to-noise ratio, we also have very good agreement with the literature. Other spectroscopic parameters from RVS are the rotation, or broadening, only for the hot stars. So this is the parameter V sin I, which is derived by the hot star module. So in this figure, I'm showing a comparison of V sin I with the literature as a function of the G magnitude. So it's separated by the cooler hot stars, so below 10,000, and then the hotter stars above 10,000. And you can see that there's overall agreement within the uncertainties with the literature. There was also a chromospheric activity index that has been measured from the calcium infrared triplet for approximately 2 million stars, and this is called activity index from the ESPCS module. What I'm showing in this diagram is a distribution of the activity or index, so which is related to the actual activity index alpha, which is given in this formula that I'm showing here, where theta is related to the temperature. The activity index is measured directly from the spectra, but it is important to account for the temperature. If you want to compare values, you need to account for the temperature, which is why you need to convert to this OR value. Now for the spectroscope, continuing with the RVS, there are many chemical abundances available for anywhere between 50,000 and 2.5 million sources. I list here all of the chemical species that you will find. And I also just show an example of a part of the RVS spectra and where some of these lines are. So I remind you that GSP spec will be found in the astrophysical parameters table. The ANN version in the astrophysical parameters subtable does not have the abundances, it is only the stellar parameters. So on the right panel, I show the distribution of, the numbers of sources for each of the chemical abundances that are available. So in gray is the full total. Do note that this is the log scale. And then in blue are what are the highest quality, the flags equal 0, the highest quality sample. In the bottom left, I show a distribution of the alpha over iron abundance as a galactic distribution. So the GSP spec team, of course, also recommend to use the flags for these abundances also, and they provide also some calibration. So in here, in this figure, I'm showing a comparison of one of the chemical abundances that is calibrated compared to the literature, where we see quite a good agreement to within 0.1 dec. So let's know for the evolutionary parameters. So you will find results for anywhere between 130 and 470 million stars. The evolutionary parameters are mg, which is absolute magnitude, the radius, the luminosity, the mass, the age, the evolution stage, and the gravitational redshift. And these are derived primarily by two modules, GSP FUT, which I mentioned earlier, but also FLAME. So again, let me just remind you of the differences. So GSP FUT analyzes the BP-ORP spectra using the atmospheric properties, and it uses also the parsec models to help to constrain the distance and the absolute magnitude. So the best results are found in the astrophysical parameters table. Whereas FLAME will analyze the output from GSP FUT and the output from GSP spec, and it will derive the radius, luminosity, and then mass, age, evolutionary stage, and gravitational redshift. So it works between 2,500 and 20,000 Kelvin, but only down to magnitude of 18.25. So the results based on GSP FUT will be in the main astrophysical parameters table, and those based on the GSP spec from the astrophysical parameters table will be in the supplement table. So here I'm showing a comparison between the radii derived by FLAME and GSP FUT, and the color code is related to the parallax signal-to-noise ratio. You can see for high parallax signal-to-noise ratio, we have excellent agreement, even though our methods are completely different. Whereas as we get to worse signal-to-noise ratio, of course, we start to see some disagreements. In this figure, I'm showing a comparison of the radius and the mass compared to external catalogs. So in the top, it's compared to some astroseismic radii from the Apogee, Pinsonneau et al., and from the bottom from the Casagrande 2011. And it's color-coded by either a difference in temperatures that we adopt in our analysis or metallicity. And you can see that there is overall agreement with these catalogs for these parameters with a reasonable dispersion. Now I'm showing a Heiter diagram showing the luminosity versus the effective temperature, but it's color-coded by age. But it's important to note that the mass and the age have been derived by assuming a prior of solar metallicity on the parameters. So for extremely metal-poor stars, one must pay pay attention. And on the very right, I show a comparison of the age that is derived by flame with the age that is derived using the exact same input data from the SPINS code, which is a published code. And you can see that we have agreement to within a half a sigma. Okay, so now I finished with the description of the parameters. I just want to give you a brief overview of the performance verification papers because it shows how we can use these parameters. So the first one is the golden sample of astrophysical parameters, where we focus on specific areas of the HRO diagram, the OBA disk stars, the FGKM, the carbon stars, ultra-cool dwarf stars, and 6,000 solar analogs, and we also analyze the spectrophotometric standard stars. Here, in this diagram, I'm just showing an example of the golden sample of the FGKM stars, where we have defined several quality criteria. And here is an example of our own analysis of known exoplanet stars using the parameters that are in this sample. The second example I want to show is from the chemical cartography of the Milky Way. And basically, we can connect the kinematic with the chemical information. So we're showing the vertical velocity versus the azimuthal velocity. And basically, the asymmetry that is seen above and below the galactic plane, and along with these substructures that have already been seen in kinematic data, are also now seen in metallicity. There's also a mapping of the diffuse interstellar band at 862 nanometers. Again, I'm showing the spatial distribution of the high-quality sample of the DIB 862, and we can see that it correlates very well with known structures in the galaxy. And finally, for the Extra-galactic content paper, this is a paper showing how we can use, not just the Cu8, not just the astrophysical parameters, but also all other Gaia archive DR3 parameters to look at what is outside of our galaxy. So in the top panel, I show an example of all of the possible galaxy candidates in the archive, whereas in the bottom one, when we use the selections on the DSC methods and the UGC methods, along with other Gaia data products, we get a much purer set of galaxy candidates. And then for the spiral arms, this is an example of a high-quality sample of red giant stars. So in the top panel, I show the stellar parameters of these stars, and then in the bottom panel, I show the distribution, the spatial distribution of these stars, but color-coded by the velocity field map with this sample of parameters. So I'm going to leave you with my summary, very dense summary slide, but it is the overview. And one extra point I would like to make is to remind you that these have been derived only using Gaia data. And it is important that we stick only using Gaia data. So if you do see differences, it is normal. We have different data. So when we compare with external catalogs, we're not saying that we're wrong or somebody else is wrong, but we're just highlighting the differences that are available. So thank you very much for your attention. If there are any questions, I can possibly answer one or two. If you are no longer interested, you can stop watching. Okay. So, yes, so the first question is, let me see, are there any variable objects for which the astrophysical parameters have been estimated? So, astrophysical parameters have been estimated for all objects down to magnitude 19. If you cross-match this with a variable catalog, you will find quite an overlap, okay? For many cases, this is fine because some of the variability is not as important, but for things like the Aurora Lyra, these are very high amplitude variable stars, and the astrophysical parameters are probably not very reliable. But you would have to look in detail at the individual sources yourself. But again, we analyze the mean spectra. So this is where one needs to be careful. So another question, a comparison of the Gala metallicity of FGK stars with the DR3 one showed that at metallicity less than -1, the DR3 metallicities are systematically off by up to 0.4. I guess it's 0.4 dex. Okay. Do you have an idea why this is the case? I believe this is probably 0.4 dex. So as I mentioned, the metallicities do have a systematic offset on the order of -0.2 dex. And as you go to lower metallicities, that there is the systematic can get worse. And this is why we encourage you, in particular for some of those, for your use case, to use the metallicity calibration tool that I presented in one of my slides. Okay, could the speaker please comment on the 0.2 dec offset? Is that coming from comparison with spectroscopic surveys? Should users calibrate the values themselves? Okay, yes, so this is a general offset compared to many different surveys. So apart from delivering all of you these parameters, we have a huge team behind the validation and checking all of these things. And so we have a team that we're working directly on the metallicities of, looking at the metallicities of all of our sources, and they did a comparison with many catalogs. So the minus 0.2 dec offset I mentioned is an overall offset. I encourage you to look at the paper on GSP-Foot by André et al. 2022, which gives more details. But again, the calibration has been already proposed by the team who know the data quite well, so I encourage you to download their calibration tool that I have shown in my slides. So the slides, of course, will remain available, and we will make them available as PDF in the comments. If you are also continuing to look for information and you don't find any information, you can go directly to the Gaia archive. There's a page on extra software tools and data that are there, and all of these extra tools that we propose are also available. Concerning the metallicities, the question was about the ones that are derived from the BP and ORP spectra. Remember that we also have the metallicities from the ORVS spectra as well. Okay, so I think that is it. If you do have any questions, so the first thing I will tell you to do is go directly to the references. In the online documentation, there's quite some technical detail if you want to know more details of things. But there are the 3 main Apsis papers, and then there are the focus papers on the individual modules. And if you still do not find your answer, then I encourage you to contact the help desk, and then they will contact us directly. So thank you very much for your time, and have a good day.